This is the Amp Hour Podcast. Released January 22nd, 2023. Episode 616. Open Source Tapeout with Matthew Venn. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Matt Venn, and these days I'm mostly focusing on open source EDA.
Silly whiz, silly whiz. I want to do the silly whiz. I love the silly whiz sound.
Yeah.
We'll get into that, of course. Welcome back, Matt. You were last on the show in 2019 at SuperCon.
Yeah.
I guess that would be episode 467.
That's
where
right.
We were talking about different things around verification and...
I think that one was about formal verification, which I'm still involved. Now the company's called Yosis HQ.
Right, exactly. So let's, people probably have seen you around for your iconic hat, if nothing else, which has migrated off just your head, but also your different things. Maybe people saw you at SuperCon this past year, 2022, where rocking a silicon wafer around your neck as well.
Yeah.
So really blinging it. But I'd say you're representing a lot of the interesting new developments in accessible silicon.
Yeah.
So what's the latest? There's a small task. Just to give us a rundown of the entire industry.
Yeah.
About 2 minutes.
Okay. Well, the latest shuttle that was taped out on the Google-sponsored open source MPW, multi-project wafer, was MPW 8, and MPW 9 is going to tape out in April. And the first Global Foundries, so that Global Foundries 180 is the second open source PDK, and that taped out in, I think that was November last year. So that was new. That was quite a big deal.
Mm-hmm.
And this year we're expecting another 2 open source PDKs.
Oh, wow.
Another one from Skywater, Sky 90.
Wow. Yeah.
More dense, a lot smaller. Yeah. So it's like one of those things where, because everything is kind of 2-dimensional, you get the square law. So if you half the size, you actually get 4 times more density.
Yep.
And then there's also the first European open source PDK coming from IHP, and I'm hoping to tape out on that as well.
Wow.
Yeah.
Awesome. Well, that's a lot of stuff going on there. So we've had a lot of people on the show in the past, including yourself, that have talked about kind of custom silicon and the progress of accessibility of the silicon process to kind of normies. And maybe could you give us a little idea of like why is this happening, right? You said this is Shuttle 9, MPW project wafer, 9. So there's been 9 kind of like group orders there, kind of like Osh Park for silicon.
Yeah.
But why is this happening? Why is there more availability here?
Yeah, it's a really good question. I think, open source EDA and EDA 4, I think, you're used to KiCad, which I think we can put in the EDA category.
Sure, yeah.
But we also have EDA for FPGAs, and we have EDA for silicon for ASICs as well, which share quite a lot in common. And there's like the very early tools like Magic, for example, which started out 40 years ago and was in use then and is still in use now. A lot of the open source tools were kind of bought out or kind of merged into the kind of the main big 3 proprietary companies now. But it's been going on all the time. I think the big reason we've seen a uptick recently is because of the Google sponsoring the lottery shuttle.
Got it. Okay.
So just for people who don't know what the shuttle is or an MPW, it's basically like even an old process like Sky 130, which is about 20 years old, the mask cost is about $200,000. So you have to put this huge amount of money, and then once you've done that, then the cost per wafer and the cost per die is much lower.
So Google's paying that; they're paying that mask cost, and then everything you're just paying kind of the
wafer cost. Yeah. So
they're paying for everything. Oh,
yeah.
Wow.
All you need to do is submit a design that is open source, and then you get a ticket to the lottery.
Got it. So they're basically Willy Wonka-ing the silicon process.
Yeah, yeah, and yeah. So we're up to 9 on Sky 130, and we've had the first GF 180, and that's all been covered by Google. And Tim Ansell is driving that, and he's already been on the podcast a few times. I think 501 might have been the last one.
Mm-hmm. Yeah, yeah. He's due to come back, but we're talking to you instead. Yeah, come on,
Yeah,
Matt over Tim. No, I'm just kidding. Tim is supposed to come back on. Tim's got a lot of things going on, and this is one of the many things he drives. Yeah,
yeah,
it's great.
yeah. So I was kind of in the right place at the right time because I had a fair amount of FPGA experience.
Mm-hmm.
I saw Tim Edwards from eFabless
Mm-hmm.
presenting an open source chip that was using the Pico RV32 RISC-V processor designed by Claire Wolf, who you've also had on a few times. And I had no idea that there were open source chip design tools. So I took one of my FPGA designs and ran it through and got the fancy GDS files out the end. Those are the kind of,
Yeah,
if you're familiar with PCBs, they're like the Gerber file equivalent,
yeah. The
but for,
Gerbers of PCBs. Yep. Yep.
yeah, for foundries, for chip
are
factories.
are they as old and stodgy as Gerbers are?
Yeah, I think probably more so. Well, I don't know.
Yeah.
I had one of the people I met at SuperCon, this guy I know called Dan Burke, who was like involved in the Valley back in the day.
Mm.
And I was talking to him about where does the terminology tape out come from? Because there's like a bit of, what do you call it when people disagree on that meaning?
Debate.
Bit of a debate, yeah. Some people say it's because you used to put the designs on magnetic tapes and then you take the tapes out to the mask factory.
Oh, interesting.
And other people are like, no, we used to use crepe tape, like actual for doing PCBs.
On like the big light tables, right?
Yeah,
Like
and
that's like the
PCBs.
iconic photos of like Weidlar and
Yeah,
leaning over these huge light tables, and they
yeah,
actually were like the masks. Yeah,
yeah. And that came from PCB layout technology, and PCB, all of that stuff came
yeah.
way before magnetic tape. So
Hmm.
tape out really comes from carrying your masks out, and the masks have been made with crepe tape that
Mm.
then
Yeah.
moved on to Rubylith. Anyway, I did a little
Mm.
interview with Dan Burke and put it on my YouTube channel. So if you're interested to hear what someone who
I think
was
we should
there,
immediately link people to the YouTube channel. What is it's Zero to ASIC?
Zero to
That's the
ASIC
name of the YouTube.
course, yeah,
Zero to ASIC course. Right.
yeah, yeah. I'm careful to make it different. There's a company called Zero ASIC, which has got nothing to do with the Zero to ASIC course. So
Got it.
got to be careful there. Although
Right.
they do a lot of good stuff. They're in the same domain.
Oh, interesting.
One of their main things is another RTL to GDS flow. So you put in your design, and out comes the GDS ready to send to the factory.
Yeah, that's awesome.
Hmm.
So it sounds like kind of a confluence of the evolution of these open source tools. It sounds like the Google sponsoring the shuttle runs, and then also driving some of the open PDKs as well. Because I remember when Tim was on the show, he was talking about the Skywater thing, and I didn't really at the time I
Hmm.
didn't really grok what the deal was. I was like, oh well, can't anyone get access to these PDKs? And the answer was not
Yeah.
really.
You used to work in a foundry, didn't you?
I worked at not a foundry at Samsung. I used to work at
Okay.
Samsung, but
Yeah.
I never had any exposure to the masks or any of the
Yeah.
design. I was basically just a process engineer,
Process
so I
engineer.
just worked in the fab. Yeah,
Yeah.
which is cool in its own right, but very
All
different.
of that stuff they don't want to share, so they
Yeah,
do
right.
this huge amount of R&D development on the
Yeah,
next process,
yeah,
and then that is part of their intellectual property and their advantage in the market. So they want to
yeah,
keep that secret, but they
yeah.
still need to let people design chips for their process. So
Right,
traditionally, you have to sign an NDA, then you get given the PDK,
right. Yep.
and
With
because
all the we will sue the crap out of you if you let this loose kind of
yeah,
thing. Right.
and
Yeah.
that's like one of the key things about making things like lowering the barrier to entry and being able to do things like training or like
Hmm.
online
Yeah.
training. If
Right.
you have to
Right. Right.
make everybody on the training course sign an NDA before they can even start
Yeah.
using the tools, that's not a great start.
Yep. Yep. And I mean, it sounds like it's also having this kind of domino effect. I'm sure that Tim is behind the scenes and others as well, like encouraging other fabs to do the same. But I could see it as you know, other people look at Skywater and I'm sure they're like, oh, look, more business, more marketing, all of that kind of, like open source as marketing is kind of an interesting thing as well. And now, like you said, there's you said Global Foundries, which is a really big name
Yeah.
doing it at 180. And then what was the European one?
IHP.
IHP. Okay. Yeah.
They're
That's
like a
great.
small research fab in Germany. But
Yeah.
yeah, I've been talking to them for a while. They're really good people. I'm actually hoping to go and visit them soon to make some videos about the process.
Oh, that'd be awesome. Yeah, I'd love to see that.
Yeah.
Yeah. It does seem like there's one additional piece in here that you did mention that I'd like to also add to the list of four things influencing this, which would be the rise of Risk Five. I feel like that is having kind of unknown, untold, unbelievable effects on the industry as well. Like I'm just continually amazed to see what's happening with Risk Five.
Yeah. Yeah. And I think one of the things that we'll see coming out of this is things like SoC builders, something like Litex, that lets you kind of snap together some bits and pieces and then be able to run that on an FPGA or tape it out. Like, you can imagine like a website with a bunch of toggle switches down the side, and you're like, yeah, I want, 8 kilobytes of SRAM, and I want eight A to Ds and 4 serial ports, a dual core RISC-V, and then you press a button that says it's going to be like $1 apart in minimum order quantity
Mm-hmm.
of 10,000 or something.
Well, and we had oh, I should look up his name. The Chiplets guy. I'm gonna look him
Oh
up real
yeah,
quick, but they kind of were talking about that, where it was kind of like a click.
yeah.
That company has unfortunately not continued on, but
That whole
Z-Glue.
thing is definitely going to be a big deal, though. And I think also, like, one of the things people say is like, what is the point of these open source PDKs that are so old? What can
Mm-hmm.
you do with them? Because everyone is focused at the absolute bleeding edge and the latest thing out of TSMC.
Yeah,
But you worked in Samsung; they have a very different process for memory, and that is a completely different
yes,
process. It's optimized very differently for something like logic. And if you're doing analog or radio, then you also
mm-hmm.
want a different process. And analog and radio and mixed signal works better at larger nodes. Analog designers have told
Sure.
me,
Yep.
I'm not an analog designer, but they've told me they prefer working
Yeah,
in,
something about capacitance and stuff like that.
yeah, or just like, when FinFET was introduced, it was introduced
Yeah,
because their transistors were getting so small, they were having like weird leakage effects.
yeah, yeah.
And that's not something you want as an analog designer.
Yep.
Yeah. So maybe a chiplet where you have, some modern process from TSMC or anywhere else for your logic. Then you've got some other process for your memory. But then you've got
Mm-hmm.
something else that could be a much older, even open source process for your radio.
Yeah. Right. 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 Yeah. And they're on the shelf and they're tested as well. I think that's the key thing there. Yeah. And it was Ming Zhang who was on the show talking about Z glue. That was the chiplet thing.
Yeah, I remember that episode. Really cool idea, though.
That's great. Yeah.
FPGA fabric that you can just drop your chiplets on top of.
Yeah. Exactly. And I think it was like the automated assembly, not the assembly, but the kind of the layout between the chiplets as well. So then you
Mm.
have kind of low impedance connections between the various elements.
Yeah, he even mentioned there was like, you have special wires just for radio.
Mm-hmm. Yep. Yep. One of the things that I wanted to kind of talk about here is because like you mentioned the chooser tool, I forget what you called it, but like the configurator style like web tool,
Yeah,
and
I don't have a name for it, but I've been thinking I should mock something up like that.
that would be a great idea. I think the thing that I always come to there though is the volume problem, right? This
Mm.
always kind of like everything in the chip industry, every industry really is like customization is great, but the volume is really what's gonna smack you in the face. I feel
Yeah,
like, and so when I look at like the open PDKs and these tools, and really just the thought of just getting the activation energy to even try this out, I think to myself, well, I don't have anything that needs the volume here. So why should I build something custom? It's better for me to spend my time going and like learning what's in the marketplace already.
yeah,
I think that as an assumption is changing, but I'd love to hear like how you see people using this and what is their motivation to kind of to start this process to get that activation energy, because I think a lot of the people listening would be on the cusp of that, right? They'd be like, oh yeah, that would be cool, but like there might be a reason that they should just try it.
Hmm. Well, maybe we can split that up into two things, because the first one is like, yeah, the volume thing. So on the MPW, or if you're if you want to avoid the lottery, you can just pay eFabless $10,000 and you get your 300 chips. So you've got like, for low volume, for prototyping or for short runs of products, it could work. But then there is, I think there still is like a gap between 300 and 10,000. So
Uh-huh.
what do you do there? And it's the same with packaging as well. It's not just the chip, it's like actually getting things packaged. Everyone is set up for these long runs, and if you don't fall into the what they're expecting, then things get expensive quickly. So I do think that's something that probably needs to get worked out. I know that global foundries are very keen on seeing like and encouraging the first volume run of an open source design, whatever that will be, and that's maybe something that's going to happen in the next couple of years.
Oh, that'd be great.
The person I've spoken to there at Global Foundries, Karthik, he's very happy to assist with silicon and support and stuff like that.
Yeah, so like kind of taking it out of the academic, maybe academic's the wrong term probably, but like low volume experimental type things to things that are actually like that have enough of a a gripping use case that like people are like, yeah, I would either buy that off the shelf or I need this for my product that already has the volume associated with it.
Yeah, because at 10,000 for 300 parts, that's still like $30 a part. So
Sure, sure.
you'd have to have a good reason for doing it, other than kind of proving something out before you do a volume run. So then to go on to your second part of your question, that was like why someone's on the cusp of doing this, why should they get involved, or or like what have I seen when people come on my course, for example, what
Sure,
they
yeah. Well, we should mention here too, if people don't know, Matt has a course where he teaches people. It's a paid course. It's very guided. You basically get through, and like he'll walk you all the way through to getting a
tape out.
done chip. Yeah, exactly. So like
Yeah, it's called
that's
Zero to
great.
ASIC, the Zero to ASIC course.
That's right. Perfect. Good callback.
Yeah.
And I think
Ching.
that like people are deciding to sign up for the course and deciding to get to the end because they have something in mind. What is that? I'm sure you've talked to them the
Yeah,
most. So
well, one thing I started, because it's only been running for 2 years. We've had like nearly 300 people on it now, and I started off with a kind of a face to face live onboarding, one to one, to kind of welcome people onto the course and set
yeah,
expectations,
yeah.
and right at the beginning to say, thanks for supporting, and you're like one of the first people to test this out. So if encourage people to give feedback and not worry if there's some rough edges here and there,
Hmm.
set expectations and so on. But I kept doing it because I really enjoyed meeting the people and asking them, what do you want to get out of it, and why do you want the course? Where do you hear about it? That kind of stuff. And I'd say good kind of 30 to 50% of people just want to understand between the silicon and running a program. So they already like maybe call themselves a full stack engineer, or they're kind of that's very well known, isn't it? Full stack engineer.
Yeah,
I
sure.
that's one of your running jokes on the
Right,
podcast
right.
as
You
well.
got to get into the silicon in order to
Yeah,
really say you're full stack. Yeah,
yeah. Now you
that's
do. Now you got to start with your AND gates and your OR gates if you're going to call
it's
yourself
all
full
it's all
stack.
driven from like nerd cred at Silicon Valley cocktail parties. I'm
Yeah,
guessing, right?
yeah. But like, say you're like a front end UI person, that's your speciality. But in your hobbies, you do websites, or you like set up a Linux server or a cloud instance or something, or you get into Arduino or Raspberry Pis or something. It's like the door is opened, or the curtain is lifted onto, well, how does that stuff work? Like going to
Hmm.
the next level down. And I think there's
Yeah.
just there's a lot of curiosity about how it actually works. And I was a contracting engineer for 10 or 15 years, and I never really thought about how the chips worked that I used. I just read the data
Mm.
sheets and wrote the programs,
Yeah.
and they worked.
Right.
And I never thought that I would design my own chips, or that I don't know, it all just felt like a black box.
Yeah.
Maybe I didn't
Literally,
have enough.
literally a tiny, tiny black box.
Tiny, 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 tiny black box. Yeah. Silvery gold,
That's right. Right.
shiny, rainbow colored box. Yeah. So a lot of people just want to fill in the details. I get like recently quite a few universities, because a lot of universities are starting to switch over to the open source tools because it's easier for doing the
Awesome.
training, or like
That's great. Yeah, because a lot of times they use like gifted stuff from like
the proprietary vendors. Yeah.
the big three, right?
Yeah, but
Like
you
they
only
because
you
the
only get those deals if you're a big enough university with enough
ah
with enough
clout.
with enough clout, exactly. And if you're
Yeah.
like a really small university or no one's heard of you, then
Yeah.
you don't get a very good deal. And these tools are extremely expensive. So
Interesting. It's like the long tail in action, huh? For
absolutely, yeah, the long
open
tail of
source serving the long tail. Yeah,
yeah, yeah, totally.
that's great.
And so now it's all of a sudden a thing that you can do. And so I'm getting universities sending their professors on the course, and then they go away and they make a VLSI course that involves a tape out.
That's how it starts, man. Like I keep hoping that KiCad gets into universities too, because why not? Like that's how these sort of things spread.
Yeah, definitely. Yeah. KiCad's another amazing tool.
What is the so you said 30 to 50% want to understand silicon. Universities are sending professors.
Yeah.
Are there any that are like commercial? Are
Yeah,
there?
I got maybe like 20 or 30% are people from a company. Like, oh, someone will buy a ticket. I'll get the notification of their email and whatever. And I'll often, before the onboarding interview, I'll just look up their domain name if it's a corporate domain name. And there's a lot of small companies that are starting to consider custom silicon, or at least using the open source tools as a way of proving a concept
Aha, yeah,
cheaply, doing
yeah,
a cheap tape out. Because even like $10,000 for a tape out is very cheap for a small to medium enterprise. And
sure,
then once they've proven something that works and they've maybe characterized it, then then at that point maybe they sign an NDA with a bigger foundry for a smaller process, and they license the tools, and
yeah. They really dig in at that point, sort of thing.
yeah, they kind of like tweak it all up and get it ready to sell. There's a big difference between a proof of concept and a product you can sell, as I'm
Yeah.
sure you and everyone listening to this is aware of.
Uh-huh. So, what, like, kind of just thinking through some of the reasons that a company might be interested, then I would imagine proprietary, like algorithms, things they don't want people to be able to extract without really digging in, slicing off the silicon and doing X-ray type stuff. I'd imagine lower power. I'd imagine lower space, like the smaller, maybe environmental type stuff, and then maybe sourcing. But I feel like that would be kind of a fool's errand, really, because of the timelines involved.
Yeah. Although, there was a time when would have been quicker to have designed your own RISC-V SoC and had it fabricated than wait for some STM32s to come in.
Yeah, yeah, that's
So
true.
you'd have to really know
I
what you're
think I
doing
think
to.
we might be on the other side of that, but
I hope so. Yeah.
yeah,
Yeah.
yeah. It is interesting too. Like the RISC-V thing, like it's still just it boggles my mind to think of all these people. Like the ping ponging of it's on a longer time scale. But like for a long time, people would be like, "Oh, I'm going to design my own processor," and then it was like, "Well, why wouldn't you just go with ARM?" And now it's moving back to like, "Well, yeah, I'm going to design my own processor. I really, really need these peripherals or this feature set or this custom instruction or whatever it is," and it is possible now.
Yeah. Although I would say that's more like SoC though,
Mm.
because there's still like not a great argument to design your own processor unless it's for a learning exercise. You should just use one of the many RISC-V processors that are like available off the shelf.
Well, I meant like some like the ones that are going big, like you mentioned, the ones that are buying tools, and for whatever reason, right? The
Mm.
one of like maybe the secretive nature of it or the custom peripheral needs, like they might not do it through these open source tools, but they might still go RISC-V. I'm sure there's many in flight RISC-V processes or processors right now that we're going to see in products in 2 to 3 years.
Yeah, I'm sure. Yeah, and there's a lot of very big names like Western Digital who are
Yeah,
kind of
yeah,
on
that's
the
interesting.
RISC-V bandwagon.
Hmm.
Yeah.
Well, let's also level set on the capabilities here, right? So, because I want to definitely get into tiny tape out as well. So, in these in the open PDK and the multi project wafers type things, like how big is the silicon, and like what could you fit in there at the various process nodes?
Yeah.
Like, what are the maximums?
So on the MPW from eFabless and Skywater and Google, you have about 3.3 millimeters by 2.8 millimeters. Just that's nearly right. It's not exactly right. It adds up to about 10 square millimeters. And that's a lot for some stuff. Like all of my FPGA designs that I was kind of working and learning with, I could fit them all in.
Like onto one wafer?
Yeah, that was one of the reasons why I like very early on started by inviting other people to join with me and put like multi project wafer. So we put 9 designs on
An
my
inception
MPW one.
wafer.
Yeah, yeah, doing that kind of even lower level integration and more designs. If you're used to FPGAs, you're kind of used to every logic element has a lookup table that you can model logic with and a flip flop and a carry chain and whatever. So you're used to getting a flip flop on every logic tile. But with an ASIC, that's not the case. You have like a blank slate and you put down whatever it is that you need. And at that point, you realize how much more huge a flip flop is compared to an inverter. It's like 6 or 8 times bigger.
Yeah.
So it really depends on what your application is and how much logic and how much flip flops you've got. One of the big problems, or one of the challenges, I'd say, is like memory density. So you don't need to use a flip flop if you want high density memory. You can use like a bit cell, which is a special foundry cell that is like the smallest they've possibly been able to squeeze it for their PDK. And you can use like a tool like OpenRAM, where you can say, I want a kilobyte, and it will build to you a like an SRAM block that you can drop in.
Oh, that's nice.
But if you use the entire area, that whole 10 square millimeters, and filled it with SRAM blocks, you might only get like 25 or 30 kilobytes. So
Uh-huh. Okay. That's a good, actually really good, because I feel like that's a good level set for what people expect out of a microcontroller. Like, so that's
yeah, it's
before.
microcontroller level, but not like enough cache to run Linux. You could
Yeah. Yeah.
you could definitely put like a
Teeny
RISC-V
tiny.
processor on there that could definitely run Linux, but you would
Yeah.
have to have off-board memory, and then you would have a bandwidth issue going through the IOs
Yes.
to the memory, and that
Right.
would be slow.
Right. Okay.
So it's more like microcontroller. Yeah,
Got it. That is interesting too, because I always complain about, I'm so used to like the growing flash size on a lot of like modern microcontrollers.
yeah,
Like, I'm just like, oh, why don't they give us more memory? And the answer is because it's expensive in geography, right? Even when you're shrinking it down.
and there's
Yeah.
still like I never really got into the ESP32. Does that use external flash still?
It has some onboard stuff, but it does use external SRAM.
Yeah, because the 8266, you had to have that external flash.
Yeah.
And
Yeah.
isn't the RP2040 external flash?
That's definitely external as well. Yeah, I know that. Yeah.
Yeah, so it's still a thing. It's like you burn so much area, and that's why things like advanced packaging and flip chip is interesting, because you use one process that's optimized for the logic,
Yeah.
and then use another
Yep.
process that's optimized for memory. But you slap them together with some interposer or whatever that means that you don't lose out on the bandwidth and the signal integrity of having it all so close together.
Right, right. And I think that, yeah, that's a really good point. And you let the people that are doing, the Samsungs of the world that are optimizing at
Yeah,
the furthest node, like, you don't need 10 nanometer flash memory. You're not going to get access to the 10 nanometer node, probably, definitely not with these processes yet,
I wouldn't.
but they are, and you can just buy that and interface to it. So like, if you said, like, if the IO doesn't matter that much, which flash is not as big a deal as RAM, right? So like, you can kind of glue stuff together that way.
Hmm.
Okay, so you could get and you are seeing small microcontroller designs on there. Again, I'm just trying to kind of give people a kind of a general idea of what's possible, what's been seen on there.
I've actually got recently started a hashtag on Twitter and
Hmm.
Mastodon called Open Source ASIC Highlight. We don't have that much stuff on. I think it's only been done like 4 or 5 times, but some of the most interesting stuff is like FPGA fabric. And there was
Hmm.
a dual RISC-V core with a built-in radio.
The radio. Wow.
Yeah,
Whew. That's
yeah, I know.
impressive.
Yeah, very impressive. I'm still waiting for that interview. When I contacted them, they're like, "No, it's not good enough yet." And I was like, "Mate, it's definitely worth
I was gonna
talking
say,
about."
I had a quick moment of panic there. I was like, "Oh crap! Did Matt tell me I should interview someone?" And I'm like, "Oh
No,
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 Matt does interviews.
no.
That's
Yeah,
that's much
I
better." Yeah,
wanted
no,
to. Yeah,
yeah, yeah.
I wanted to interview them
That's
about it.
good. You should be talking to them because I have no idea who they are. First off.
Yeah, and if you go on the eFabless website, you can like scroll through thousands of entries to the lottery. Not all of them get
Ah,
taped
cool.
out, but you can see
Yeah.
the kind of stuff that people get up to.
Yes, and I should mention we had Mohammed on the show as well from Eat Fabless.
Yeah, number 503.
I haven't caught up with him in a while. Yeah, yep.
So
So
prepared.
yeah, that would have been like me furiously typing for like
Yeah,
2 minutes. Matt's just like, yeah, I made a sheet for it. So
yeah,
thank you, Matt.
you're
You're
welcome.
very organized. You're very organized, and both in your course and your just the. I really loved your recap video. You did a
Oh
recap
yeah,
video of 2022,
yeah,
and like it really highlights. There's a lot going on in this space. It's great.
yeah, yeah. I had to really trim it down as well. I had to like throw out the least good half, and it was hard drawing that line.
Oh shoot! Now people are listening like, oh, I didn't make the video. Oh, no.
Yeah, yeah.
Yeah.
So much stuff is happening.
It is, and like, and people are excited about it too. It's great. I mean, like, it's really great. It's is there going to be like a I don't know, like a conference around this sort of thing? Are there conferences? I know there's like a RIS5 kind of
Yeah,
thing, but not.
I did one last year called Open Tapeout,
Okay, all right.
and I was thinking of doing another one. I'm now a board member of the Fosse Foundation, and I
What's
brought it up in
Fosse?
the yeah brought it up in the most recent meeting, saying why don't we do like because there's now conferences are kind of coming back up. There's like
Yeah.
there's Latch Up.
Oh yeah.
Well, FOSDEM is really soon, but there's not so much hardware in FOSDEM. Then there's Latch Up. There's OSDA and Date, and there's more stuff coming up. But I like online conferences because they're much easier and cheaper to organize, and
Yeah, but they're less engaging. That's the downside.
they're less engaging. Yeah, that is the downside. I agree. There's like less opportunity for networking, but yeah, they've got ups and
Who
downsides.
goes to conferences for the talks, man? Come on, like
Yeah, you just
you
watch
go
them
to
streamed
conferences for
later.
the hallway. Yeah,
Mm.
exactly,
Yeah,
exactly. You know, you
yeah,
Fosse is free and open source silicon. Is that right?
yeah. That's right.
Okay.
Yeah, it's a foundation.
Yeah, that's cool.
And we were thinking of maybe like running a an online conference because there's like the face to face one in on the West Coast coming up,
Hmm.
Latch Up. But I won't make it, and I won't make it because it's like too far to go, basically. So
Yes, you are based in Spain, correct?
yeah, I'm based on the east coast of Spain in a city called Valencia, and online conferences, yeah, mean that people can attend all over the world, even if they don't have the ability or the money or they don't
Right.
want to travel
Sometimes you just got to get up at 3 in the morning. You know.
or watch it when it's streamed.
Yeah.
Yeah, I don't know. I find 6 p.m. Central European time quite good because
Yep.
that
Yep.
works for Indian time, and there's a lot of stuff going on in India as well in this space.
Oh, interesting.
And but it also works for Pacific time.
Yeah. Yeah. That's
Mm.
like 9 a.m.
Yeah,
Pacific.
sorry, Australians. Sorry, Greg.
Yeah. Yeah. That is the most common webinar time I see is like they're always doing
Yeah,
9
or
a.m.
yeah,
Pacific.
yeah. And I
Yeah.
for the weekly calls for my course, we do it at
Yep.
6. Yeah.
Yep. 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 What's going on in India? India.
Well, I mean, India's been like a place where loads of chip design work has been outsourced to. So you might have like a design team in California, but you might have the verification team, which might be
Oh,
even
interesting.
like the same number or double the number of people all working out of India. And I think, we're not there yet. Like, it's no one should think that the open source tools are kind of capable of challenging the proprietary ones. They've had like
Right.
20 years lead and like
And a lot of
hundreds of
money.
billions of dollars poured into them.
Yeah.
It's going to be a while.
Yeah.
But that doesn't mean there's not niches now that can still work. For example, education, and
Sure.
there'll be more stuff coming online. And I think one of the exciting things is you could come from a place where you don't have the resources for these expensive tools, and you could do something creative and groundbreaking that nobody had thought of because you've got availability to the tools in a way that you never had before.
Yeah.
Or you train up and you know what you're doing, and then that makes it easier for you to land a job in one of these bigger companies.
Yeah. I think that's right. Yeah, and I mean, like, accessibility is really important in these cases, and I think about like we're in the hardware industry broadly, right? Calling the PCB, system level down to silicon level. It's it's weird because it's further. It started sooner, and yet it's much further behind the software world. In terms of open
Yeah.
source and
Yeah.
accessibility and stuff like that.
Yeah. Why
But
do
I
you think
think
that is?
I think because of just the investment required, right? Like the
The money investment.
yeah, exactly. I mean, there's hard money investments that had to happen, and as a result, there's culture of secrecy, like you had mentioned earlier. But what we're seeing now is one, I think the software industry is leaking into the hardware world, right? That's thanks to folks like
Yeah.
Tim and his coworkers at Google, and they see business benefits from doing that sort of thing. This is like this is off the cuff as well, like we
Mhm.
usually do here. But I think then as well we see an excess of capabilities, right? So like these fabs, even though you mentioned like it's 180 nanometer fab, which is I don't know what 20 generations behind. I don't know what the generation number. Yeah, it's 20 generations behind or I guess that would be you divide by 1.5. So say 12 generations behind the leading edge, which Global Foundries also does, right? And it's like, but they still keep it running
Yeah.
because it's already been paid for,
That
and so now that
investment. Yeah.
becomes yeah, excess capacity. So it's like it's not zero marginal cost like
Mm.
I think some of the software stuff gets, which is an oversimplification as well. But it is excess capacity that then there's other benefits to having the marketing and just opening it up to new business as well.
Yeah, and seeing what happens. Yeah.
Yeah, yeah,
And
exactly.
I mean, I know after education, which, I don't know how big that market really is
Yeah.
or how many wafers education would buy. But I think another one that is likely to happen, it will be in the security space where you want
Yep,
transparency and inspectability. So
yep.
if you think about all the cloud services that is being offered, people are, like Amazon or Microsoft or whatever, they're even building their own servers. And what they want to guarantee you as someone that runs a software as a service company or something is that you control it all the way down and it's only going to be running your software and there's no kind of man in the middle between you and the hardware.
Right, right,
And so
right.
they
There's
do
no.
these things with these little root of trust authentication
Hmm.
chips.
Yep.
And it doesn't matter if those are old or big. What matters is that you trust them. If there was like an open source design for a root of trust chip that everyone could inspect, and then it was made, the GDS was made with an open source inspectable toolchain, and then it was taped out on like an open source PDK, and then someone even like imaged a few of the chips to prove that they were the same thing that was sent in, then you've really got like a level of trust and inspectability that is
Yeah.
difficult to get otherwise. And that kind of thing might be good, like one of the niches where open source chips will actually start to have a market share.
Hmm. Yeah, that's really interesting. That's, I mean, the root of trust stuff. That's what we had Laura from Oxide talking about a little bit.
Yeah,
I think if
exactly. Yeah,
yeah,
that was a great episode, and she discovered like a whole bunch of problems in that chip that they reported back to NXP. I think it was.
that's right.
Um,
Yeah, the
yeah, I
55
reached out
S69
after
FF.
that episode and was like, "Hey, do you fancy making your own one next time?"
That'd be great.
Yeah,
Yeah, yeah. If they do, that'd be. I'm sure that, like, yeah, like you said, that's. It is interesting to think about. Like, I mean, you and I are talking right now on across hundreds, thousands of miles of just computer infrastructure, right? And we
yeah,
don't think about the stuff that's down below, but there are people that are like that need to understand that entire chain because at some point there is a critical there's critical pieces of the infrastructure that if they don't understand that, then they literally don't have the keys to their own kingdom.
yeah.
And I think you're right about the niche piece as well. I don't expect TSMC to dive into this anytime soon because there's just so much money involved.
Hmm.
And
DSMC actually have a great educational program running already. I found
oh
out.
yeah,
Yeah, when I
interesting.
spoke to a Taiwanese professor, they have like,
Uh,
if you're at university doing VLSI in Taiwan, you basically get free silicon.
wow, that's great.
Yeah,
Yeah, yeah, and I think that is that's how you make a company that lasts for many years, and you basically build your own pipeline of
of
student
engineers. Yeah,
of engineers. Yeah,
yeah,
that's great. Let's talk about tiny tape out. So now we're basically like going down into the quantum realm, right? In terms of the size of chips that people are making.
yeah. We should make sure we get some time to mention silly
Silly
whiz as well.
whiz. Yeah, and those are tied together.
Yeah, well, they're kind of
Uh,
complementary. So yeah, tiny tape out. I can't totally recall where the idea came from, but it's an extension of the work that I do in my course, where we get like 10 or 12 people's designs and join them all together using a tri-state
Uh-huh.
bus, and then put that all into one chip and tape that one chip
Uh-huh.
out. So then we only have to make one application or pay for one chip, and then we share the results back between the course members.
Can you explain the tri-state bus real quick? Like, so you basically have like a chip select for each design, or how does that work?
Yeah, yeah, just like
Oh,
SPI. Like
great.
if you've got like a bunch of SPI devices, they've each got an
Uh-huh.
active line, and normally their inputs and outputs are high Z, as you say in America. I've actually been
Instead of
converting
you're not
myself
saying
to
Zed or
American
what?
English. It's an interesting one. I mean, it's like I stopped spelling analog with the GUE at the
Yeah.
end, and then I was just wondering, where does it
Uh,
end? Am I going to
oh,
like? I mean,
next.
American English is what the world speaks, isn't it? It's not
Oh,
English
sure,
English. It's
sure.
American English. So
Well, have you started saying y'all yet?
y'all, we use high Z inputs.
Well, I mean,
Y'all.
you're in Spain as well. So interesting. I'm speaking of education. I'm taking Spanish tutoring,
Oh
and
yeah, como estás?
the vosotros form, right? So vosotros is like how you say plural version of you, and there's not really
Yeah,
that, in English it's like you guys or all of
yeah,
you, but the best, I think the
yeah.
best translation is y'all. So Spain, which uses
Y'all,
vosotros, and Latin
everybody.
America doesn't normally use vosotros, or some
Mm.
of Latin America doesn't. Yeah, you already have y'all. It's vosotros.
Yeah, so we have all these designs
uh,
tri-stated, and they only kind of activate their outputs once they've got the active line,
great.
and then they have control of the 38 IOs the chip
Oh,
has.
cool. So then, do you have to route the? How do you route the actual IO to each individual chip? Then it's just like,
The auto router does it.
oh yeah, really?
Yeah,
What is the
yeah.
I guess I haven't tried this yet. Like I said, I haven't felt the pull to do it yet. But how much is there automation in there? Right? Is it all like, are people mostly?
Yeah, the digital side is really
Mhm.
automated. So you take your hardware description language, like Verilog or VHDL, are really popular common ones, and you throw it in one end of one of these tool flows. Like OpenLane is the one that I use most often, and that's the one that's developed by eFabless. The core of OpenLane is formed by OpenRoad, which is a separate project that used to be DARPA funded,
Yeah, yeah.
and they do a lot of good work. OpenRoad, check them out.
I think when Mohammed was on the show, he mentioned that. He explained a bunch of that. Yeah.
You mentioned that, yeah. So yeah. So OpenRoad kind of forms the core tooling, like the placement, and the STA, the static timing analysis
Yeah.
tools, and
Okay.
this kind of stuff. But the number of tools involved in the flow is, I don't know, maybe between 10 and 20 different tools.
Wow.
So
Okay.
kind of all
Yeah.
like plugged together in a long
Yep.
line. And if everything goes well, you put your Verilog in, and at the end you get your GDS out.
Awesome.
So you don't do any manual routing. It does it all for you.
And then you get to visualize it as well, right? You get to visualize like,
Yeah, you can then look at it, yeah, and do a 3D render and post it on Twitter.
yeah,
That's
that's
what I
what
do.
you got to do, right?
Yeah, actually, if you try Tiny Tapeout, we also have like a really cool 3D viewer that runs in the
Yeah.
browser, so you can kind of zoom in on the standard cells and see how all the wires are connected.
Yeah. And so, what is the difference then? So, in Tiny Tapeout, you are not writing Verilog, or you are writing Verilog?
So the target audience of Tiny Tapeout is like absolute beginners, people not even like most of the people on my course have like use a computer or have done some
Hmm.
programming. The idea with Tiny Tapeout is we have enough learning resources for people that have never done digital design before. And I'm collaborating with Uri
Yes. Yeah.
from Wokwi. You had him on in number
That's
599.
right. Yeah. That
That's
I
right.
think Uri might be the. I don't think he sleeps. He just seems like he's just always making new things. It's
He's very good fun to
yeah, I
work
bet.
with because I can like come up with ideas in a spec, and then like a few hours later or minutes
Yeah.
sometimes,
Yeah.
I've got something that I can experiment with and
Yeah.
play with. And we'll get onto Tiny Taper sorry, Silly Whiz in a
Yeah.
bit, but we're using Wokwi, and that was one of the things you spoke about with him in that episode,
Hmm.
which is a really nice interactive browser-based tool where you can build, like you can drop an Arduino
Yeah.
in, put your LCD in your button, write some firmware, and then simulate the whole thing.
I think the thing is, it presents as an Arduino simulator, but it's just like the most powerful engine underneath. It's like a Ferrari engine underneath like one of those like play school plastic toys that my daughter rides in. You know, like the little cars. You know.
Yeah, it has a really good model of the
Yeah, yeah.
chips. And I met him in one of the Hackaday
Yeah,
remoticons, and he did a
yeah.
talk about when he added the
Mhm.
RP2040 to Walkway. So then you can run your designs on that. So we basically added a set of 10 components and gates, all gates, flip flops, that kind of stuff. And you build your digital design out of those. You can use LEDs and whatnot to kind of debug the state of various things. And then we added an API, not really an API, but a way of requesting it to dump you a netlist in a Verilog format. So then it tells you,
Yeah.
here are all the gates, here's what they are, here's how they're connected, in between a kind of input and an output plate that gives you 8 ins and 8 outs. And then we have a GitHub action. So you template my GitHub repository. It's got an info.yaml file, and then you change the Walkway ID to your ID. It fetches the Verilog netlist, runs it through OpenMain and the open source
Mm,
PDK, and generates you GDS and a kind of report file.
yeah.
And in the report file, you've got a list of the standard cells that we used and a 3D model of the little design, which Tiny Tapeout 1, I think, was 120 by 120 microns. So it's like enough room for kind of 500 or 600 standard
Yeah,
cells.
yeah. So that's actually really good, a good kind of like audio visualization. I feel like too, right? So people start with just like an inverter and a NOR gate and an AND gate connected together however they want. But the inverter has a set of transistors that are defined in the
Yeah.
standard cell, right? And basically, because you know the abstracted inverter shape or inverter function, you can then assign that to all of these gates that it represents. And then you tie that to the set of gates that represent the NOR gate, however people are connecting these things together. And then it just kind of processes all the way through, right? I feel like that's kind of the abstraction layers are deep on this one, you know?
Yeah. But in a way, if you're using Walkway, you're actually closer to the hardware
True.
than you are if you're using a hardware
Yeah,
description language,
right.
because you are actually drawing a
Right.
schematic with components. And I think that's actually a good way to start, because if you're a programmer, one of the hard things about coming to a hardware description language is, especially one like Verilog, where it kind of has a C like
Yeah, yeah.
syntax.
Yeah, it's not really describing all that much hardware, right? It is, but it's not.
Yeah, you're writing a program that's going to be executed on a general purpose computer, one line at a
Yeah,
time,
yeah,
or like one instruction, however that line is
yeah.
broken down into its instructions. When you're designing hardware, you are designing that
Yes.
machine. And that machine, if you need something to be done sequentially, you have to first build a
Mhm.
sequencer. Otherwise, everything's just going to happen all at
Yes.
once, just like an electronic
Yeah.
circuit.
Yep, yep.
It's all happening at once. So, yeah. Well, with Tiny Tapeout, that's
That's
the
true.
idea, is that it's like for real beginners, people who've never done any digital design. But for Tiny Tapeout 1, we actually ended up with maybe 30 or 40% of the designs were in some HDL or other. And we ended up changing the GitHub action so that there was like one version for Verilog and one version for Amaranth and one version for VHDL or whatever.
What's Amaranth?
It's a like what's called an HLS, high level synthesis. So it's like a bit higher up than something like Verilog.
Oh, interesting. So you said LightX earlier. Is that the level
Yeah,
Amaranth's at?
that kind of level. Yeah, yeah. There's another one called Chisel.
You know what would be useful is to draw a map. Is there a map of all of these different tools of like what's built on what? Because if not, that would be really useful.
Yeah, that's a good idea. I'll write
Yeah.
it down.
That's
Um,
really good actually, because I feel like people do kind of they want to operate at different levels, right? Some people say I just want to blink an LED. Some people say I want to actually see I want to control which inverters are involved in blinking that LED and
yeah,
right and there's reasons to learn each of them, I think.
yeah. And one of these kind of arguments you see all the time is like, oh, to be a real programmer, you've got to understand the full stack, which I think is
Mhm.
nonsense. But I think if you want to be like a master programmer, then it can help to understand more of what's above you, who's consuming what you're doing, and what's below you, what the
Yeah.
abstractions that
Yep.
you're basing your work on are based on, because a deeper understanding of those things is going to, on one side, mean that you deliver better stuff to the people that you're using your output, and on the other side, you're making better use of whatever is you're standing
Hmm.
on. But yeah, it's like I can explain how a computer works down to a standard cell or a MOSFET, but I can't actually explain to you the quantum effects of how electrons
Yeah.
tunnel
It's
in a
Flash. Yeah.
flash
Yeah.
cell. So, life is too short.
Do you even electron volt, bro? Come on.
You got to. Time is like the most valuable
Yeah.
resource. You've got to choose where you're going to spend
Yeah.
it. And when I was young, I had infinite time and no money, so I just did everything from
Yeah.
scratch to
Yep.
learn it. And now I have infinite money and no time.
Yeah, it is. I feel the pull. I feel that same pull these days. I don't know if I would say I have infinite money,
No,
but
no. But yeah, you got to choose. You got to be wise about where you
yeah,
spend your
yeah,
effort.
definitely. Hmm.
Yeah.
It is one thing that I've seen is that the people that do understand more of the stack, like above and below them, like you mentioned, kind of looking up, looking down. It may not be critical for design, but it damn sure helps for troubleshooting. It's like,
Yeah, you're just like aware of like, because those abstractions
yeah,
break.
yeah,
You know, it's like, oh, it doesn't work
yeah.
like this. I thought, it was just digital 0 and digital
Hmm.
1, and there was
Yeah.
no like in between things. It actually is a real voltage
Yeah.
that might not be
Yep.
exactly one or
Yep.
the other.
Yeah.
Yeah,
It
yeah, all kinds of
it does.
problems.
It is a smacking. That's the 2 a.m. problem right there. When you're like, what am I looking at right now?
Yeah, and it makes no
Yeah,
sense with the abstractions that you're
that's right.
used to,
Yeah.
and you have
Yeah,
to
it
kind
breaks
of
your mental model. Then
dig
you
down a bit.
have to reconstruct your mental model, and yeah, it's
Yeah,
oh, what fun learning. Isn't learning fun,
yeah.
Matt?
Well, I think that we're all drawn to solving
Yeah,
puzzles in this
yeah,
area.
yeah.
That's like one reason why we're here, so that we stay up till 2 in the morning trying to
Hmm.
solve it.
Yep. So okay, so tiny tape out basically. People can they still do it?
Yeah, so Tiny Tapeout makes it even easier to submit a design onto the shuttle. And the other thing is we're not using the lottery shuttle. So, because I think one of the things that is starting to become frustrating is like the last shuttle, there was a 1 to 3 contention ratio. So you could put a lot of work in, submit your design, and then you're not even guaranteed that you're going to get it made.
Got it.
With Tiny Tapeout, we have like for Tiny Tapeout 2, we had 250 slots,
Aha. Yeah.
and
Got it.
we sell those slots. So you can, all the educational material is there, and you can use it, and you can learn everything. All the content is free and not behind a paywall, unlike my course.
How much does it cost for a tiny tape out slot?
We've got two different price levels. One is design only, which is $25 or was. Yeah, I don't know. We may need to change the price. We'll have to see what happens. And then $100 gets you your design on the chip on a PCB.
Oh, nice.
So you get the whole thing, and it's kind of being tested. And the other nice thing with Tiny Tapeout is you've got all the other designs.
Yeah,
So
so you get to play around and
I
see what other people did, and
yeah, and when you submit your design, you have to like have some basic documentation in place, and then we aggregate that all together into a kind of custom data sheet for
that's
the
fun.
chip. So when you get your PCB with your chip on it, you've also got like a basic understanding of how all the other designs work and how to test them and what to expect.
So then, okay, so they get the PCB with the chip on it. Is it activated for
Hmm.
their specific chip? Like, is there like a pull down for their chip select or what?
There's a little 8-pin dip switch, and you set it to the
Oh,
ID of your
nice.
project,
Yeah, 250
and
slots,
that
huh?
activates that
I guess
one.
there's six
Yeah,
extras in there doing some controlling, huh?
yeah, yeah. Don't set it
Yeah.
to those, or it'll
Yep.
blow
Yep.
up.
Yep. Oh, that's super cool. Wow.
Yeah, if you go on the Tiny Tapeout runs page, I'll just paste that in the message here. You've got a picture of the die, so you can kind of see how we've fitted them all together, and you can see the ones with a lot of purple.
Hmm.
That's routing on a higher metal
Uh-huh.
level, so it gives you an idea of like the more dense
Got it.
designs.
Yeah, because some of these are really, really simple things like blinkers and similar type of thing, right? But some people are also
Yeah, some might have like I had like a system on there, so if there were less than 10 standard cells, it would be like a warning that I'd have to wave. So I'd check out their design and be like, yeah, they really just have got an AND gate in there. Fine, that's cool. They just
Just
want
want
to
to be
have an
part
AND
of it.
gate.
Yeah.
Fine,
Yeah.
no, I have no
Yeah.
problem with that. And then another one, they're really struggling to fit it all in. Like we had a RISC-V processor on here, Chris.
No way. Wow.
Yeah. Do you know Olof Kindgren?
Oh, the name sounds familiar.
He's an award-winning hardware designer.
Okay. There we go.
And yeah, so he made Serve, which was like which won a kind of a RISC-V prize. They ran a competition a while back, and it was like the smallest RISC-V processor. It's a bit serial, so it executes serially. So it has a 1 bit wide register. So you have to execute 16 times or whatever to get a 16
It's
bit.
like reverse pipelining. Yeah.
Yeah, but so it's very slow, but it's very small. So Greg Davil actually mentioned him earlier. Took Serve and adapted it for this and taped it out on Tiny Tapeout too.
That's awesome.
Yeah,
It's almost like a tiny Kickstarter, right? Like
yeah,
you get the token, which is the end chip and the you're working on a board, but then you also get like the kind of we're all this in this together sort of thing. That's pretty great.
yeah. It was really fun doing it. We have a Discord, the Tiny Tape Discord, and it's that really kind of pops off when it's getting close to tape out time.
That's
Yeah,
great. Yeah,
people helping each other out.
yeah.
Really cool to see that.
Community and culture, like that stuff, it matters. Like that's how you keep people interested, and that's how people learn from one another. I feel like too. So that's great.
Yeah, no, you don't burn
Yeah,
out if you're trying
exactly.
to run these
Yeah,
projects.
yeah.
Yeah.
So let's get to SillyWiz. So SillyWiz
Oh
is now
yeah, let's not
separate
forget
from
Sillywiz.
SillyWiz, uh, from
Yeah,
Tiny
so
Tapeout.
Sillywiz is designed to fill in the gap. So Tiny Tapeout, if you follow the lesson plans, it builds you up from like the most basic digital logic to like simple machines, like a padlock that only opens if you set the code right. And SillyWiz aims to kind of explain how, like, from silicon to an inverter, a CMOS inverter. So, how do you draw a resistor or a capacitor or a MOSFET or an N type inverter or a CMOS inverter?
So it's another abstraction layer down. Now we're actually building a standard cell or modulating a standard cell, basically, right?
Yeah, yeah. So you have like your canvas, and then you can draw shapes on that canvas in a number of different layers, like metal, polysilicon, N diffusion, P diffusion, and by combining shapes and patterns, you build up these little functional blocks that form the basis of all digital logic design.
Awesome. Yeah, I think
Yeah,
we mentioned on the show, and like the fact that there's sliders on there is like I think I said this when we talked about it on the
yeah,
show, but just like the being able to modulate and like change your environment and see what the result is without having to like redraw. Man, I still remember
yeah. It's
my
crucial. Yeah,
analog my
it's
analog course where it was like we were drawing with colored pencils on not graph paper, like the tiny box, like the 1 millimeter by 1 millimeter box
mhm.
paper. It's just like the worst way to learn. Not the worst way, but it was just so inaccessible for me personally. And
Yeah,
this would have been,
yeah.
I don't know. It's just I have a lot more knowledge now, but it's really much more accessible.
Yeah, so it's in the browser, so you don't have to download anything, and you can do and undo. So that's nice, and you can turn on and off layers, so it's less confusing. But you're right. The thing that makes it like feel amazing to play with, if you've ever, and probably a lot of people haven't, but the people who are listening who have spent time kind of drawing something out with Cadence or K layout or Magic, or and then extracting the circuits and then simulating it and then getting the graph up is that all that like each bit takes a bit of time and there's you have to learn each tool and you have to sequence them. And with SillyWiz, you can increase the length of the gate on a MOSFET, and you can and it just within milliseconds, like not even a noticeable amount of latency really, you see the graph changing. And that gives much more of an opportunity for learning intuitively how these things work. And I think that that is really important for making it easier to learn things.
Definitely. Yes.
Yeah, quick feedback. Yeah, it's kind of ironic that the thing that you're designing then takes like at least six
Yeah.
months for you to get back in your
Yeah.
hands.
Yeah. Why does that take longer? I mean, so like it I'm just going to couch this in my experiences at Samsung. You know, wafer in to wafer out was 30 days. What is the six
Hmm.
month aspect? Like, where is the largest chunk of that being spent?
Well, one part of it is you have to wait for the MPW to be ready to run because they don't run them all the time. You have to catch the right shuttle. They only normally would run them like 4 times a year.
Okay,
And then it's going to be one of their low priority jobs.
got it. Okay, so it's in the holding cell whenever anybody else comes through.
Yeah, because they're probably only going to run like a lot of
Hmm.
20
Yeah,
wafers for an MPW because
yeah.
it's just for hardly any parts. Skywater is slow.
Well, slower. I think these are not like, in the timescales we're talking about. This is a miracle these things happen at all.
Yeah,
But like compared to high volume kind of
yeah,
things, yeah,
yeah, it's not like a big. The Skywater shuttles. I think that's like a kind of a fairly low priority for
hmm.
them. The the, the Global Foundries one should take six
I
weeks
see.
for wafers out,
Got it.
but packaging takes the same amount of time.
Interesting. Okay.
So then you got to ship it to get packaged, and it's got to get packaged, and then it's got to be like mounted onto PCBs and tested, and then it's got to be shipped.
Yeah.
So with Global Foundries, it's conceivable to think that you could get your chips back in 3 months,
Huh. Okay.
and I sincerely hope that will start happening soon.
Yeah. Right. Because these are innovation cycles as well, right? So if someone was designing, a commercial product, they would want to be, like the cycle time really does matter for being able to try different things, optimize, update, all of the things that you do
Yeah.
in a
I
PCB.
mean, ideally, you want that result back so that you can learn from it before you
Yeah.
send the
Yeah.
next one.
I need to see all the
But
mistakes I made
yeah,
on my
but a
bench.
lot of people don't have the luxury to do that.
Yeah.
You've got to like send off your next iteration, and you may have errors that you don't know about.
Yeah.
And that's something that really bit us hard with the Google Skywater shuttles
Mhm.
MPW 1
Yeah.
to 4 because there was this critical problem, a hold violation problem. And if you're a chip designer, you know that a hold violation is not something you can solve by
Mhm.
turning the speed down or anything. It's really difficult to work around,
Yeah.
if not impossible.
Yeah, and you did manage to get yours blinking. I remember
Yeah,
you
but it
were
was a real.
yeah,
I mean, it was like a reverse engineering contest to capture the flag. It
yeah,
was
yeah,
definitely. I wouldn't have done it if I hadn't had so much kind of not exactly riding on it, but by that time I'd kind of the course went so well that between the course and the other contracting jobs that I did, I'm just kind of doing full time open source EDA now,
awesome. Yeah,
and I really, really wanted it to work, so I was willing to pour hours into it.
yeah,
But if you'd done this as a kind of hobby in your evenings and then you got chips back that were really difficult to bring up, I'm not surprised that not many people managed it.
yep,
And I was really only, I mean, I might have worked out on my own, but it was really Sylvain Minot's work, TNT,
yeah.
who kind of, he made a really fancy system that used an FPGA to model the memory that the Pico RV32 RISC-V processor on the ASIC executed out of. And then by counting the number of instructions it executed, you could see how well it was running.
Wow.
And then it can modulate the core voltage. So you could plot a histogram of core voltage versus how many instructions the Pico RV32 managed to run. And then you could choose like an undervolted amount that had enough instructions that could then execute enough instructions to set up the GPIOs correctly.
Oh wow.
That was only half the story,
Oh my
but
god.
that was, yeah,
Yeah, that's
really good engineering effort
yeah.
on his behalf. That kind of, I've got that board on my desk right now. It's like instead of just being one PCB in an ASIC, it's like a,
It's like
a
a
layer of four different PCBs.
yeah. The monster grows. Yeah, so Van was also on 467, the first show that you were on. So yeah,
Yeah,
and I
yeah.
got this.
He's actually working on Tiny Tapeout 3 at the
Oh,
moment.
awesome,
We're taking some of the money from Tiny Tapeout 2 and paying Sylvain to help execute an upgrade so we can run the whole thing faster.
awesome. Yeah, I mean,
Yeah.
all right, real quick, I want to talk about Silly Wiz a little bit more, and then I'd like to ask you about the tape out process.
Yeah, we've been going for a while, haven't we?
We have, yeah.
Yeah.
So Silly Wiz, there's the video. It's you have to be part of
Mhm.
Tiny Tape Out the course in order to access it. Because I remember I saw a link of it at SuperCon, and I was like, "Oh my god, everybody needs to see this!" But now it's
Yeah.
part of the course for sure.
It will be available free open source, definitely.
Uh huh.
Don't worry.
Got it.
It's just that without knowing what you're doing, it's difficult to drive, and
Yep.
it needs some extra support, or it's going to be frustrating.
Got it. Yep.
So we're doing like another round of UI tweaks, and I'm writing the lesson plan material at the moment with support from some analog IC gangsters that I know.
Hmm. That's great.
And then when that's ready, we'll launch it, and we will launch it first to Tiny Tapeout and Zero to ASIC course
Yes.
people, as it's one of these kind of things that you have to get into if you're like doing
Yeah.
if you're like self-employed. It's like
Yeah.
you have your patrons, and you give people a reason to patronize you
That's
by
right.
having advanced access to things.
Yes, I think people should go to tinytapeout.com and subscribe to the email list so that you can hear about the Silly Whiz first and then also hear about Tiny Tapeout 3 when that's ready. So, and
Yeah,
then you'll also get some helpful emails about going through the course, the free course stuff, and then maybe also Matt's more advanced course.
yeah, exactly. Yeah, sign up
Yeah.
for the mailing list. That'll
Yeah.
be
That's
that'll be
great.
great. And then you'll be the first to get access to SillyWiz when it's available.
Yeah.
Yeah.
All right. So we've been talking, like you said, we've been talking for like an hour plus now. I do want to ask real quick about like the tape out process, right? Because it's not like, so if I submitted a design, click done, I'm happy. I just wait my 6 months and I get a chip. You have other stuff you have to do with it, right? So like the actual like buttoning up a design and like sending it off to the fab, that's non-trivial.
Break it down a bit more for me, Chris.
Well, like, so what does it involve? So when you say tape out, what does that actually,
Hmm.
what is the actual, so I think about sending off a
Well,
PCB.
I press the record button on my reel-to-reel recorder here, and
And then the
program the
magnetics, yeah, they just take care of
magnetic
it.
tapes,
Yeah.
and then I send them to
Yeah.
Skywater.
Right,
Yeah,
right.
and that's called a tape out.
Right, exactly. You just say, first there's an inverter, and then next to that, actually, no, below that, there's a NAND gate, and then NOR.
No, because what I'm really doing is I've got a big light box here, and using very fine tape. I've taped out the whole design. I send that to Skywater.
I'm an artisanal taper.
I'm an artisanal taper.
Yeah.
Yeah,
Okay,
I only use the most black of black
that's
tapes.
right, right.
Yeah, and the whitest of white backgrounds.
So, like, when I think about the PCB process, right, it's gotten easier and easier to send off a PCB, a set of Gerbers, right, zip them up, send them off to the to
Yeah.
the JLC or whoever, and they tell
Mm.
me if I do something wrong. Is it the same for sending it to Skywater, or what does it take to actually get that last step done?
Yeah, and there's abstraction here as well, right? Because if you were, say, going on a shuttle, a TSMC shuttle or a Global Foundry shuttle, that you were just interfacing directly with them, or you were going through an intermediary like Europractice, then you would need your design, but you would also need it to be in a pad ring of all the GPIOs and the ESD protection and whatnot. There's a little bit more extra stuff, and then you've got to, like, depending on the packaging of your chip, like the MPWs that we've got access to a wafer level chip scale package, so they're like little BGAs. So you need a little bit of extra information about how the packaging and the balls are bonded and all this kind of stuff. But for us, all of that stuff is handled by eFabless. So
Aha.
the
Okay.
bit that we submit is just the 10 square millimeters that fits into a standardized harness, and that harness is called Caravel, and that has like the pad ring, the GPIO, the ESD protection, the layout for the balls of the package, and everything else. So for me, tape out is a bit easier than if I was interfacing directly with Global Foundries, because I don't have to deal with that stuff.
Okay. That's an interesting. Okay, so that's kind of what I'm really just trying to make like in my mind like an analogy for, like I said, PCBs. So in this case, eFabless is acting like the board house, and then the equivalent of like the people that are actually doing the silicon is like the people that are dipping the boards at the board house, right? They're like actually imaging and you think about the process of making a PCB. That's now the silicon processing through all the machines and all the steps that happen there.
Yeah. I mean, have you ever visited a PCB house?
Only through Scotty's videos.
Okay.
Yeah.
Because one thing I was surprised at when I visited one is that they don't just take your file and like slap them straight on the masks or whatever. They inspect everything, and they make little changes, and
Oh
they
yeah, yeah.
like might move stuff around, or they might, like, PCBWay especially are pretty good at
Hmm.
spotting errors and feeding back.
Yep.
So
Yep.
you could maybe say that like eFabless are like that. They're kind of
Yeah, yeah, yeah.
dotting the I's and crossing the T's, and then they send it off to Skywater, and Skywater is the actual. the people that make the chips.
Yeah, the dipping of the stuff into the Cooper chloride, right? Like that's
Yeah,
yeah, it is at a board house. Usually they're together, right? Whereas in this case, there is like a eFabless is like the front of house kind of dealing with the digital
yeah,
files, and then the actual process control that's just at the fab.
yeah. And you'd have to be quite big if you wanted to deal with someone like TSMC.
Yeah,
So
right.
normally you have to go through an MPW service. It's run by an intermediary like Europractice, and
Oh, there's others. Yeah. Okay.
yeah, they will help like a to kind of do the aggregation and help with the packaging and help with a bunch of other stuff. Yeah.
Got it. Yeah, because a full lot of like like I think about like even 10 by 10 millimeter wafers or sorry chips. You could fit a lot of those onto a 300 millimeter wafer, and then
Hmm.
the lot size is usually like you said 20 to 25. Like that's 25 fits in a FOUP, I think, and then just there's just so much. That's so many chips to get through.
Yeah.
Like that's just a really big order.
But yeah, so but for an MPW, they're all like that's it's split between 40 people.
And so an MPW would that be multiple designs on one wafer, and then you have 25 of those
Yeah,
wafers?
exactly. That's exactly what it is.
Okay,
So it means you only make one mask
got it.
of that includes all 40 people's
Ah,
designs. So
right,
you
right, right,
split that 200 grand across
right,
40 people.
right. You wouldn't want to
Yeah,
have, yeah, that makes sense. You wouldn't want to have one design replicated many, many times across one wafer. You'd want to have all of this IP shared on a mask because each wafer is getting a shot of that mask.
exactly.
Yeah,
Yeah.
yeah,
Or
yeah.
probably being stepped multiple times. Yeah.
Yeah, right. That makes sense. Okay,
Yeah.
okay. That
Yeah.
Huh. And then when they dice it up then, so the slicing and the dicing, it's just like
Mhm.
they have to be able to within the now larger unit cell, right? The lot
Know
of
which one is whose and
yeah,
then package them up so that I just get mine and not yours.
that's right.
Yeah.
Okay. All right, that
Yeah.
makes sense.
And then what we've done with Tiny Tapeout is like the next level down. So
Yeah,
in
right.
our one slot on an MPW, we have 250 slots.
So how long until I can buy a single transistor on a single wafer that I get delivered to my house?
Well, if you'd have put in an order on,
The finest artisanal NMOS that I
well, if you want to talk about the finest artisanal, most NMOSes, and you're talking to the wrong guy, you want to talk to Sam Zalouf about that.
uh-huh, that's right. Yeah, yeah, and you got to hang out
Yeah.
with Sam at, SuperCon, right?
At the SuperCon, yeah.
Yeah,
I gave him one of my
I
hats.
saw that. I saw that. Those
Yeah.
are a fun that is a fine hat. Like I said, I like the culture that you're building around this. It's weird, it's fun, it's cool. It exclusive because it's difficult to understand. But it's totally like
Well, that's what we're trying to change
that's
that
right,
bit.
and
Yeah.
exactly, and to this audience, the people that are listening right now, you could totally do this. Like, I think I could do it
Definitely.
too. I'm just lazy. Uh,
You
yeah,
definitely could do it, Chris,
yeah.
yeah.
And one
Yeah.
more time, can you give a pitch for like why someone might want to learn this stuff? Like, just help people dream right now, Matt, because you, like I said, we are Willy Wonka-izing this process. So, who are the dreamers of the dreams? to quote Gene.
Yeah. Well, anyone that is interested to kind of know how deep the rabbit hole goes
Hmm.
with how electronics and chips work, and anyone who thinks that open source is going to eventually dominate chip design just like it's dominated software, and they want to be like on the early wave, now is the time to start.
Okay, I like it. Matt, is there anything else that we missed that we definitely should have mentioned?
Let me look through my very organized list of
I mean, it
notes.
is a really good list. I will drop other links. Matt sent me a bunch of links too. Like I said, like he said, he linked me to all of the relevant shows. Like this is next level guest, folks. This is like Matt. Matt has his stuff together. If I ever make a chip design, I dream of getting asked to be on the Zero to ASIC show. I have no reason to be interviewed on there, but if I ever am, I can't even
You're
imagine
going to
how
be like a
organized
special
that
guest.
process. Yeah, yeah. I'm just
Yeah.
I'm just the
No, I
tourist,
think that's it.
you
I
know.
think that was, yeah. Yeah. We covered
Yeah,
everything.
awesome.
Yeah. Yeah. Subscribe to my YouTube channel and don't miss
Yeah.
the X-ray tomography that we're doing at the Zurich Particle Accelerator this
Whoa,
year.
awesome, awesome.
Yeah.
Yeah,
Teaser.
I cannot wait. I think if anyone's going to start anywhere, I will directly link people to the video that Matt did of 2022, like the recap. If you watch that
Hmm.
and you're not excited about open source silicon, I'm going to say you're not enough of a nerd, and you should introspect. You should get excited about open source silicon because of the stuff that Matt and all the other people in the community are doing. It's really, really exciting.
Thanks, Chris.
Thanks for being here, Matt. We'll talk to you soon.
Yeah, cheers. Bye.